Everyone to our next Learn and Share. Today we have Nakul from UCLA, PhD student from UCLA, and also a PSC grantee who has been working on implementations of authenticated garbly. And today he's going to talk to us about BitGC. This is something he talked to us about internally, and it was so exciting that we asked him to share it with everyone, and he graciously agreed. So Nakul, thank you for your time, and the mic is yours.
Yeah, as Ali said, hi everyone, I'm Nakul, a PhD student at UCLA. I'm researching secure multi-party computation, or MPC, and today I'm going to talk about BitGC, which is a recent work by authors Hanlin Liu, Xiao Wang, Kang Yang, and Yu Yu. I'll first introduce Garbage circuits as a general tool to do MPC, and we'll look at its first construction by Andrew Yao, which is more than 30 years ago. Then I'll introduce BitGC, first its semi-honest version, and explain how this protocol drastically reduces the per-gate communication cost for GCs, which is often the bottleneck in practice. Finally, and this is time permitting, I'll talk briefly about why semi-honest security might not be good enough in practice, and how garbling protocols, specifically BitGC, can be upgraded to achieve so-called malicious security. Let's start with what is MPC. MPC is a protocol or a suite of protocols that allow mutually distrusting parties to compute any function on shared data in a privacy-preserving manner, which is without trusting each other or anyone else with their private data. In an ideal world, if you had this entity that everybody trusts, you could very easily do this task. Every party just sends that trusted entity their private data. He or she will compute the function and broadcast only the output, forgetting everything else that it knew. MPC is using cryptography to replace this trusted party. In a little more detail, an MPC protocol just looks like people sending each other a bunch of random messages, which somehow reveal nothing but the output of the computation. The goal is that these random looking messages somehow suffice to allow the parties to compute the function. They get the output of the function in a way that preserves computational integrity. So they get the correct output and input privacy. You don't leak your sensitive information to other parties. But what exactly does random mean? If it's random, how does it help you compute anything? If it's not random, aren't we leaking something? How do we formalize this? It turns out the security of MPC is formalized in a super fascinating way. As I said, an MPC protocol looks like something that we have on the left. Parties send each other messages. But for a moment, imagine living in that ideal world that I spoke about earlier, where we have this trusted entity, everybody trusts him, could send him their inputs. He'll compute the function for you and broadcast the output. Note that in this ideal world, each party would literally only see their input and the output, nothing else, no random messages either. Now, we say that an MPC protocol on the left is secure if these random looking messages in the real world give you as much information as you'd obtain in the ideal world, which means nothing, right? Commonly, an MPC protocol is secure if there exists a simulator living in this ideal world that can just look at the view of a party in the ideal world and use that to simulate the view of the party in the real world. And with this, for all intents and purposes, as a user or a developer, you can just view MPC as this trusted entity that allows secure computation on shared data. It's clear that MPC would be tremendously useful where you want to, in any situation where you want to collaborate on data in a privacy-preserving way. Some examples are statistical analysis. So say organizations hold sensitive data, they want to pull it together for some kind of analysis, or biomedical computation. Patient data can be very useful for research, but it's often legally protected. MPC can be used to still gain insights from the data without ever revealing the raw data. And MPC has also been used in satellite collision detection, where governments don't want to reveal the exact position of their satellites, but they still want to know if their planned trajectory might lead to a crash. And finally, MPC can be very useful in AI. Consider just one example is where you have a server that's holding the weights of some large language model. You have a user with a sensitive query. The user wants to query the model such that the server doesn't learn its private query, and the server doesn't want to reveal its weights to the user. And here you could use MPC. But with so many potential use cases, why has MPC not been adopted at a much broader scale? And the primary reason for this is its practicality. Current MPC protocols incur a significant slowdown in runtime. Recall those random messages that I mentioned earlier. They actually turn out to be really long random messages, and generating them can be computationally intensive. On the bright side, though, MPC protocols have been rapidly improving over time. And the protocol we're going to see today introduces ideas that I think might be very useful for making MPC practical in the future. Today, we'll focus specifically on MPC for two parties, dubbed 2PC, and only look at so-called gobble circuit protocols. A GC is a tool that was introduced by Andrew Yao, as I said, 30 years ago. And since then, it's taken on a life of its own, and today it's the most popular way to do constant round MPC. By constant round, I mean that the number of rounds of back and forth communication between the parties is independent of the complexity of the function that you are evaluating under MPC. Remember, I said MPC is a general tool. You can use it for any function. And because it's constant round, this is especially useful in high latency settings. And it's usually the most efficient way to do MPC there. At a very high level, this is how a GC protocol works. We have two parties, the cobbler on the left and the evaluator on the right. And they start by agreeing on this Boolean circuit representation of the function. For example, just consider a circuit that consists of AND and XOR gates. This forms a complete basis for computing any function. These gates are Turing complete. Now, a GC protocol proceeds as follows. The gobbler on the left looks at the circuit, and to each internal wire of the circuit, he associates two keys representing false and true. So the green represents false here, the red represents true. Next, he uses these keys to generate these encrypted truth tables, more on that later, for each gate of the circuit in a way that pairs of input keys. So if you look at the AND gate with input wires A, B, and output wire D, pairs of input keys should encrypt the corresponding output key according to the logic of that gate. So the 0 and the 0 key should encrypt the 0 output key, 0 and 1 should output the 0 output key, 1 and 1 should output the 1 output key, because I'm looking at the AND gate specifically. For the time being, I'm not going to specify more details about how this encryption works. We will look at that in more detail when we specifically consider Yao's protocol. Then these encrypted truth tables are sent over from the gobbler to the evaluator, and this comprises most of the GC communication cost. This is the thing that we're going to try and optimize for in our protocols. Next, we want a way for the evaluator to obtain input keys that allow her to decrypt these encrypted truth tables and proceed inductively through the circuit. So we start by wanting her to obtain input keys corresponding to a chosen input of her choice. So the next step is that the gobbler and the evaluator, they engage in this oblivious transfer protocol. OT is a primitive that's used widely throughout MPC. We won't get into the details of how it's implemented here, but the functionality that it achieves is that it lets the gobbler send over key pairs. So for input wires A, B, C, he'll send over these green and red key pairs. And he can send over, he could send over the matching keys, the keys that match the evaluator's inputs, while one, hiding the complementary key from the evaluator, and two, also hiding the evaluator's input from the gobbler. For example, here, if the evaluator picks input 110, she'll receive red, green keys corresponding to wires A, B, and C, but she doesn't look at the green, red keys corresponding to those wires. Now the evaluator holds keys corresponding to these inputs. She has the encrypted truth tables, and she can inductively proceed through the wires, as I mentioned earlier, and she can now output the key gate by decrypting with her input keys. So for example, with two red keys, she will decrypt a red key for wire D, and then with the red and green key for the next gate, she will, because that's an XOR gate, so 1 XOR 0 is equal to 1, she'll again decrypt the red key. Finally, she'll obtain some key, either 0 or 1. She won't know that yet, but then pooling that information with the gobbler's information, she can now decode the output of the circuit. In short, this is what happens. The parties use OT to transfer input keys. Then the gobbler sends over this GC material, the main cost of the protocol, to the evaluator, who proceeds gate by gate and obtains output keys. Very importantly, note that for each intermediate wire, the evaluator obtains exactly one of two possible keys and does not learn whether this corresponds to 0 or 1. That's important. She doesn't learn whether this intermediate wire value is a 0 or a 1. Here we can see a red key or a green key, but she doesn't know that. We want to keep that hidden from the evaluator so we don't leak any extra information. He only decodes the output keys information along with the gobblers, along with the information that the gobbler has. Now let's look at a specific GC protocol. That's Yao's protocol, the first one that was introduced. I've already gone over the framework of how GCs can be used to achieve general 2PC. So it just remains to fill out certain details, like how are these keys picked, how are gates encrypted, and how they're decrypted. This is what the gobbler does. He starts by picking two random bit strings. We'll use a length of 128 bits in practice as a true and false key for each wire. And then he creates this table of ciphertexts that encrypt output keys using input keys, as I said. So specifically for an AND gate here, look at the first table that I have. Keys A, I, and B, J should encrypt output key D, I, and J, which is what you'll see if you look at the 4 rows. So that once this is sent over to the evaluator can decrypt the appropriate output key with her input keys. Here, just to explain the notation, H is a hash function. It's modeled as a random oracle, and without getting into any details, all this means is that with input keys AI and BJ, you can compute H of AI BJ. But if you don't hold either of these keys, that just looks like a random value to you that you can't guess. So given two keys, the evaluator can decrypt exactly one row of the encrypted truth table. That's how we've arranged it right now. But remember that the keys that the evaluator holds, they correspond to the underlying wire values for that wire. And we don't want the evaluator to learn whether this is a true or a false key. So the protocol as such, if you just send these tables over, it's still insecure because the evaluator, she'll end up learning which row she can decrypt, and that might leak information about which inputs she has. So one fix is just have the gobbler randomly permute these rows, send that over to the evaluator, and then she'll try decrypting each row until she gets a valid decryption. This way, that decrypted position won't leak anything about the logical values. Before proceeding to the next GC protocol, I'm going to talk about two optimizations to YAOS protocol, which are free XOR and point and permute. These are pretty relevant for BitGC, and that's why I'm going to take 5 minutes to look over these optimizations, and they're very clever tricks as well. We'll start with free XOR. Now, as it turns out, very surprisingly, there's a way for the gobbler to set the wire keys in a slightly smarter way so that you actually never need to send over any material for XOR gates. XOR gates are free. Now, the protocol cost only depends on AND gates. That's cool, right? Earlier, I said that the gobbler, he picks random 0 and 1 keys, but now I'm going to modify the protocol and say that he only picks random 0 keys, and he picks this one global offset, we'll call that delta, and then he sets all the 1 keys to be the 0 key XOR that same delta. Also, he doesn't pick all the 0 keys at once. Instead, he now proceeds through the circuit in a gate-by-gate order. And then for XOR gates, he won't pick that. He won't pick the output key of that at random. Instead, he'll set the 0 key of the output to be the XOR of the 0 keys of the input. Note that I've dropped my 0 and 1 subscript notation here. If I just use the letter, that's the 0 key. If I say XOR delta, that's the 1 key. The reason this thing helps is now the evaluator can actually compute the correct output key just by XORing the 2 keys that he has without needing to encrypt any table. One quick example, say that the evaluator has A and B plus delta. She doesn't know that this is the 0 key and the 1 key, but say that we know this is the 0 key and the 1 key. She just XORs the two, gets A XOR B XOR delta, which is C XOR delta because of how we set it, which corresponds to a value of 1, which makes sense because 0 XOR 1 should be equal to 1. This basically just boils down to XOR being a linear operation, and it works well with serious shared data. So we only need to worry about the non-linearity, which is captured in the AND gates. In fact, we have like optimized circuits for computing AES that try to have as many XOR gates as possible and minimize the number of AND gates because that's most efficient for GC protocols. And for the next optimization, remember earlier I said that the evaluator will try and decrypt every single row of the table, but this isn't ideal. Somehow, it would be great if there was a way for the evaluator to know exactly which row she could decrypt in a way that doesn't leak any information. There is a way to do that. What we have here is that the cobbler, along with picking these input keys, now he picks random bits. We call these permutation bits. He picks random bits for all the wires. So he picks pi A and pi B for wires A and B, and he uses these to randomly permute the truth table. So without getting bogged down by the notation here, if the gobbler picks pi A is equal to 1, you just swap the first two and the last two rows of the table. If you pick spy B is equal to 1, you swap the odd and the even rows of the table. Along with this, we now arrange for the evaluator to somehow learn these masked values, which I've written on the right. These masked values are the underlying value, which we keep hidden from the evaluator, XOR with the permutation bit, which again, we keep hidden from the evaluator, but the gobbler knows. So individually, these two values should be kept secret from the evaluator, but it turns out that it's okay to leak the XOR of the values. And it's incredibly useful to do this because now the masked value that the evaluator holds points exactly to the row in the encrypted table that she has the labels to decrypt. Um, it's best to see an example here. So let's quickly walk through one example. Say that the gobbler sampled pi is equal to 1, pi b is equal to 0. So we flipped the first two and last two rows, but we've kept the odd and even rows unswapped. And assume that the evaluator also holds masked values. So suppose she ended up with labels A0, B0 here. With the permutation bits that we've set, this would correspond to masked values 1 and 0. This corresponds to the third index of the encrypted table. And if you look at the third row here, this is exactly the row that she can decrypt with A0 and B0. And I'll acknowledge this is something that can take time to digest. You need to probably work out an example by yourself to be convinced that this works for all the rows. But for the purpose of this talk, just understand that the gobbler these are used to randomize the truth table in a way that the evaluator can directly point at which row to look at. And importantly, the evaluator never learns the permutation bits picked or the underlying wire values for the labels that it holds, just the XOR of the two. Now, a lot of effort has been spent over the years to optimize this even further, improve the communication efficiency of these protocols. And that's usually measuring the number of bits per AND gate because XOR gates are free. In Yao's protocol, with the optimizations we discussed, we had the gobbler send over this entire truth table of 4 rows. So we sent 4 ciphertexts. This is all, each of this is an encryption. So we sent 4 ciphertexts of material per AND gate. Over the years, this has been with like really clever tricks. This has been reduced to 3 ciphertexts, then 2, and then even 1.5. But for security reasons, each of these ciphertexts is still set to 128 bits. So this is still about 200 bits of communication per AND gate. BitGC, the work that we're going to look at today, it reduces this per gate communication to just 1 bit per gate, which is like a 200x improvement per gate, right? That's crazy. It's important to mention that BitGC does make some strong assumptions. Specifically, it uses the so-called learning with errors assumption, whereas the other works only use a random oracle. They use a hash function with a couple of extra assumptions, and that's modeled as a random oracle. But still, this LWE assumption is very well studied. It's the same one that's used for homomorphic encryption, if you've heard of that. And if you haven't, it's something that we'll look at soon. So a really exciting result. How does it achieve this like super impressive improvement? It does that by working a slightly different cobbling framework. So let's look at a very high level difference between previous works and BitGC without going into details right now and exploring that slowly. Previous works, for each gate, you had the gobbler encrypt the correct output key with like all the possible input key pairs, arrange that into this truth table, send that encrypted material to the evaluator. This consists of most of the cost. And then the evaluator uses her input keys to decrypt those output keys. This work uses a different approach. Now the gobbler, he uses his input keys to encrypt output bits. More on that later. This what output bits, how are these enough? We'll look at that in more detail. But he now encrypts output bits rather than like encrypting that output key. And before all of this happens, what happens is this the parties engage in this pre-processing phase where they distribute correlated randomness. This uses constant communication independent of the circuit being computed. Then using one correction bit to the evaluator who can locally produce these encrypted bits. So these bits were computed by the gobbler. The encrypted versions of those bits were never sent over to the evaluator. The evaluator had her own preprocessed material and she corrected that with this one bit of communication to the encrypted bits that she needs. And then she'll use her input keys and the encrypted output bits to somehow produce the output key. right? The idea is that the evaluator has like preprocessed material, and then from there, just one bit is enough to reconstruct the entire garbled material and then proceed with evaluation. In a little more detail, we'll start with BitGC starts with a computationally more expensive pre-processing phase, independent of the circuit being computed and independent of any input. So this can be done beforehand, before they even wonder, they agree on which function they want to compute. Um, this uses low communication. And what happens is the gobbler, he picks a random seed, he encrypts the bits of the seed with a secret key that only he knows, and he sends over the encryption of the seed to the evaluator. The evaluator, he uses homomorphic encryption, more than that in the next slide, to homomorphically expand this encrypted seed into a lot of random encrypted bits. These bits are known in the clear to the gobbler, and these are known in encrypted form to the evaluator, but they're random bits. So these random bits clearly can't consist of the GC because it can't be like completely independent of the circuit. Yet, these random bits plus just one bit of information per gate from the gobbler is enough to generate this GC of encrypted bits, which can then be used by the evaluator to use input keys and decrypt the output key. For the next few minutes, we're just going to look at, we're going to try and understand some more details about these steps. For now, appreciate that we've moved to a different gobbling framework. We're not encrypting keys, we're encrypting bits, and we're just using one bit to correct an unfixed GC that the evaluator has. So homomorphic encryption. Oh, yeah, Andrew?
Yeah, hey, I just wanted to clarify for a second. So I thought for a minute, and now I think maybe this is not true, but maybe you can clarify. It sounded a bit like the way this scheme works is we fundamentally sort of recover what we would have had in the type of garbling scheme we were talking about before, or at least some variant of that. And then we can proceed and sort of use that, but achieve the same thing with less communication. Is that roughly true or roughly false? Like, is it the same? Do we recover the same kind of thing, or is it fundamentally a different thing that we're recovering through this technique?
Yeah. Pedagogically speaking, it's a good framework to have, that we are recovering something very similar to the previous scheme, and then we're using this trick of like having correlated randomness to just use one bit to correct it. The gobble circuit that we are recovering, it's different than the one that we've seen before. It's similar to the in the table, I said there was one thing that used 3 ciphertexts instead of 4. It's actually very similar to that, but we're using these encrypted bits instead. It's an okay framework to have in mind, but I don't think that's exactly what's happening. And I think as I continue with like the more explanation about how this works, I think you might get some more clarity.
Okay, cool. Can I ask one quick question?
Yeah.
The wire labels that we recover in this system, are they like 128 bits corresponding to the 120 bits of compute security as well? Yeah, they are.
Yes. Yeah.
Okay, cool.
I think so. Yeah.
Okay.
Yeah, I think that.
Cool. All right, thank you.
Okay. Yeah. Back to homomorphic encryption. So homomorphic encryption is it's an encryption scheme that supports computation on encrypted data. And this work just uses somewhat homomorphic encryption, which supports computing simple functions on encrypted data. By simple functions, I specifically mean functions whose circuit representation is low depth. And this is much cheaper than fully homomorphic encryption, which can support arbitrary functions, but that requires an expensive bootstrapping step to control noise growth. Also, this is why we don't just substitute MPC with homomorphic encryption. They both do achieve a similar functionality of being able to compute on private data without actually seeing that private data. But FHE is still not as practical as MPC. Yet I'm saying that this BitGC protocol, it uses, BitGC is used for MPC, and I'm saying it uses homomorphic encryption as a subroutine. Crucially, BitGC will only use homomorphic encryption in a way that the noise growth is independent of the circuit being computed. Therefore, we don't need any bootstrapping, and this is still completely efficient. in terms of computational cost as well. With that, we're ready to dive a bit deeper into how BitGC works. I will skip a lot of details here. I'm going to answer two main questions. What are these encrypted bits? Answering Andrew's earlier question, we said this is GC consists of encrypted bits. What exactly do they look like? And how are they used to decrypt the output key? And how is one bit of communication enough? Both parties here, they started with encrypted random bits. I said that can be produced with constant communication. And then just one bit of communication per gate is enough for the evaluator to reconstruct the GC. How do we do this? Because these are the two main ideas, I'm going to reiterate it once more while taking a look at this high-level overview of the protocol. This is the previous slide. So I said there's a gobbler. He uses his input keys and pre-processed bits to generate a GC of encrypted bits. What are these encrypted bits and how are they used by the evaluator to decrypt the correct output key? Second, I said that these encrypted bits never need to be sent over. You just have the evaluator. The evaluator, she has her own correlated randomness, and she can just fix this with one bit of communication to these encrypted bits and then proceed with evaluation. How is this done? We'll answer both questions one by one. We start by looking at what are these encrypted bits that are needed to make this protocol work. And I'm going to start by introducing a key technical component of BitGC, which is an extension of homomorphic encryption to support something called distributed decryption. Technically, this is achieved by a simple extension of HE. It's a simple extension of one scheme that implements HE, which is called the GSW scheme. And we're actually only going to use distributed decryption in the context of the specific EV algorithm. So let's just look at it as a high blocks right now and see what it achieves. So yeah, unboxing what's going on here. We have an algorithm that takes in 2 keys and 3 encryptions of bits. It takes 3 ciphertexts. And what it achieves is it allows parties that hold encrypted bits and shares of a secret key. Okay, so the bits here, they're encrypted under a secret key delta, and the parties don't need to know delta here. They can have these shares of, because the first thing is a share of I times delta, the second thing is a share of J times delta. So they can hold shares of this, and they can use that to obtain shares of a linear combination of the bits. Okay, so neither party here needs to have the secret key, and that's why we don't expect them to be able to decrypt the exact bits. But still, with the shares of the keys of the key that they have, they can use that to decrypt shares of a linear combination of bits. This does seem a little bit contrived, but it turns out to be exactly what you need for the evaluator to obtain output keys from input keys. And it's simple to achieve this functionality. So let me show you how this algorithm is used now. Recall what I said earlier, the evaluator, she has to use these encrypted bits along with her input keys to get the desired output key. And compare this to how in Yao's GC, she used the encrypted truth table and her input keys to get the desired output key. I'm going to skip a lot of details here, and I think questions regarding more details here, we can probably postpone them to the end. It's very interesting to work out these details, but for now, let's just look at what we get from here. So the gobbler, he picks these bits, based on those permutation bits that I spoke about earlier. So each of these bits is a deterministic function of those permutation bits for the 3 wires of the gate, pi A, pi B, pi C. He sets them as such. It turns out this is what allows the algorithm to go through and work out how we want it to. And he sends, for a second, pretend that he sends these encrypted bits across to the evaluator. Then, if he also sets one of the output keys according to this EV algorithm, then if the evaluator runs the EV algorithm on the keys she holds, it turns out that this algorithm magically works out to give her exactly the output key that she should get here. She can just compute EV on her input keys and these encryptions, and the math works out to give you the output key that the evaluator needs here. This should convince you, modulo, a lot of calculations that need to be checked, that the encrypted bits and the magic EV algorithm achieve the gobbling task. Okay, but in this picture, I still have a gobbler sending over these encrypted bits, and that's too much. That's too costly. We want it to be just one bit of communication per gate. How can we do away with this? how can the gobbler communicate across these encrypted bits to E using only one bit? This is where the pre-processed encrypted random bits and homomorphic encryption come in handy. So along with the input labels, now remember we have arranged so that the evaluator, she has encryptions of random bits, and these random bits are known in the clear to the gobbler. So we set these exactly to be the permutation bits, pi A, pi B, and we also generate one additional random bit, we'll call that RC, an encryption of a random bit for the evaluator and the random bit for the gobbler. And recall that to run her algorithm, she needs these. Oh, yeah, Ali?
Nakul, I encourage you to use the marker to point to where you're talking about.
Of course, yeah. So we have the evaluator hold these encryptions of random bits pi A and pi B, and we also arrange for her to have an extra encryption of a random bit RC. Recall that these encryptions of B1, B2, B3 are what the evaluator needed to be able to proceed with the evaluation algorithm. We want her to obtain these encryptions without the gobbler communicating across these encryptions. But these three, B1, B2, B3, going back to the previous slide, these were just functions of the permutation bits pi A, pi B, and pi C. And these functions are pretty simple to compute. It's just one gate, so like an AND gate and an XOR. This is where homomorphic encryption comes in handy. So we inductively arrange that the evaluator has permutation bits for input keys that she already holds. So say that she has encryptions of pi A and pi B at this point. And if she had an encryption of pi C as well, she can just use the same logic that the gobbler used here, but along with homomorphic encryption to obtain B1, B2, and B3. She doesn't yet have pi C though, but this can be communicated with like exactly one bit of communication. We had this other random bit RC. We have an encrypted version of RC that the evaluator holds. The gobbler knows pi C, and the gobbler also knows RC. He has that initial PRG seed in the clear, so he knows all the randomness that the evaluator has encrypted forms of. He can just send over this correction bit, pi C XOR RC, over to the evaluator. And now the evaluator will look at her encrypted RC, XOR that with this correction bit homomorphically, and obtain an encryption of pi C. Now she has encrypted versions of pi A, pi B, and pi C, and she can use those to homomorphically compute encryptions of B1, B2, B3, and then proceed as before, use the evaluation algorithm, and get the output key. So other than the pre-processing step, for this to work, we need only one bit of communication per gate. And doing a quick cost accounting here, the communication here, as I said, is dominated by that encrypted seed that was initially sent and these correction bits. So we have lambda, like the security parameter. So 128 ciphertext that need to be sent for the encrypted seed. The size of each ciphertext is quasi-linear in the security parameter. It's quasi-linear with supposedly large constants, but it is still independent of the circuit size. So it's slightly more than quadratic in the security parameter, asymptotically speaking. And you need one correction bit to be sent over per gate of the circuit. So the total communication in bits is like size of the circuit plus slightly bigger than quadratic in the size of the security parameter. And the computation here turns out to be dominated by this homomorphic evaluation of the PRG in the first step and this EV algorithm. You can set parameters so that you can use this so-called low complexity PRG, and that gives you an amortized cost of O1 homomorphic operations per gate, adding both the PRG evaluation and the EV algorithm. So these are the costs of BitGC. And the next question is the security good enough? And why not? Okay, so all I've shown right now is that these protocols are secure and they hide the data that you'd want to hide, so long as parties behave, right? Now, going back to Yao's GC, the algorithm that I described the gobbler uses to gobble these gates, the gobbler could actually incorrectly gobble the gates so that the evaluator expects to obtain the output label corresponding to an AND gate for this first gate with A, B, and D as the wires. But instead, the gobbler used the logic of an OR gate to gobble this, and now the evaluator has ended up with this wrong output key. And remember, we don't want the evaluator to learn which output key she has. So this is something that's not detectable by her. And this could lead to the wrong final output, and this could like even leak some sensitive data that you don't want to. You might think that one fix here is just attach a zero knowledge proof of correct gobbling here. But actually, even this is susceptible to the so-called selective failure attack. So looking at the right here, the gobbler can do this really nasty attack, which is selectively gobble rubbish for some rows. So for the third row, he just puts like random bits and gobble all the other rows correctly. Now the evaluator might be able to detect this and abort. So like if the zero knowledge proof at this step fails, she might abort if and only if she had masked values corresponding to 1, 0. If she aborts, the gobbler now knows that she had masked values corresponding to 1, 0, and he also has the permutation bits pi a and pi b, and this now leaks the real wire values x and y using the fact that the evaluator aborted at this row, which gives these masked values, and the fact that the gobbler knows what pi a and pi b are. Luckily, it's true that the evaluator cannot cheat here, assuming that initial OT is done in a maliciously secure way, which can be done pretty cheaply. The evaluator has been given the GC material, and at worst, she can follow a different evaluation strategy and then ends up with rubbish outputs that don't map to any output keys. But by the security of encryption, she can't learn output keys for any inputs that she doesn't have. So upgrading this protocol to be maliciously secure, and I'll explain what that means in a second, that task mostly consists of handling a malicious gobbler. Similarly, for BitGC, one thing that the gobbler can do is just send the wrong bit to the evaluator. When the gobbler is supposed to send pi-c, x, or rc, you can just flip that bit, send that to the evaluator, and you can, again, a simple calculation here would show that the evaluator would then run the EV algorithm and end up with the wrong output key that she's supposed to. So you could flip an AND gate to a NAND gate here. And again, this might not seem like a big thing, but you could end up like computing a different function that leaks more information than your desired function wanted to leak. Note that everything that I've said, I have argued why it's not good enough to have that security, but this doesn't technically violate the definition that I provided earlier, where we'd assume both parties behave honestly. So instead, what we have to do here is we need to upgrade our definition of security itself to allow for malicious behavior from the other party. So it's formalized as follows. In the real world, we allow the corrupt party, which is the adversary, to send arbitrary messages now. We don't require that that Alice follows the rules of the protocol. She can send arbitrary messages, and we handle these messages in the protocol specification. So we might say that if Bob receives a rubbish message here, just abort the protocol, right? And now security again says that a simulator living in the ideal world should be able to simulate the view of a party in the real world. And notice the difference between the semi-honest definition and the malicious definition. Here we assume that both Alice and Bob follow the protocol, and then we say that their views be simulatable using the output, so they shouldn't learn anything. In this case, we're saying that even if Alice deviates from the protocol, we still require her view to be simulatable. So she can't deviate from the protocol and learn something extra like we did in that selective failure attack. In that, she was able to learn something extra, and we want to protect against attacks like that as well. The main takeaway here, if a protocol is maliciously secure, then if an honest party follows the specs, so follows the rules of the protocol, runs the correct code, they are guaranteed input privacy, irrespective of the other party's actions. And this is a much stronger and perhaps more practical definition of security. So how do we achieve the stronger notion of security? I'm going to very briefly look at this in the next 10 minutes. In gobble circuits specifically, there's a framework called authenticated gobbling. What this does is it distributes that gobbling process between the evaluator and the gobbler so that no one can mess with the GC to like leak sensitive information. What I said the gobbler could do earlier, he can't do that anymore. And then it also performs an authentication check afterwards. So the parties check that they actually did compute correct gates. So you can't flip an AND gate to an OR gate, for example. This ends up like specifically addressing the two issues that I raised earlier, but you can then prove that these two steps actually guarantee you malicious security as well in the way that I defined it earlier here. So let's look at these two steps in a bit more detail. Recall I said that earlier, a gobbler in the semi-honest protocol could incorrectly gobble an AND gate as an OR gate, for example. And to protect against these, we do a correctness check at the end of evaluation. And now recall that point and permute technique that I introduced earlier. This is also where it comes in handy to know that optimization. In that technique, we had the evaluator holding masked values for each wire, which is the internal value XOR the permutation bit that the gobbler holds, right? Actually, I've flipped the order of who holds what here. The masked value should be held by the evaluator and the permutation bits should be held by the gobbler. Sorry about that. Either way, they end up with these simple XOR shares of the underlying wire values for which we want to check that they satisfy the relationship without leaking those underlying wire values, right? This is done in 2 steps. You first authenticate these shared bits. I don't think we have time to get into how exactly the authentication works, but basically this means that there's now a mechanism to prove that you haven't tampered with bits at the end of the protocol. You can prove that, hey, the bit that we agreed on using, that is the bit that I used in the protocol. And then to check all of these gate relations, you can just take one random linear combination of these authentication tags, and that's enough to verify correctness. In a little bit more detail, say that you want to check these 2 constraints specifically. So you want to check that the value of VD is equal to VA and VB, and VE is equal to VC XOR VD based on the gates of the circuit. So what you do is you first replace these bits in the protocol. So throughout the protocol now, instead of having a bit, you have an authenticated bit. That's what I've denoted in the double angle brackets here. And you use those, and then both parties sample these random values, chi1, chi2, and they check this single relationship. If this relationship holds, then over the randomness of chi1, chi2, with high probability, the individual gate relationships also hold. So your final correctness check just reduces to checking that one thing is an authenticated 0 bit, which is cheap to do. So that's the authentication after evaluation step. And the other step is distribute the generation of this GC. Recall that in the previous authentication check that I mentioned, it happens after evaluation. So it still doesn't protect against the selective failure, which can be an abort during the evaluation of the protocol. This framework basically it views gobbling as this function of randomly picked wire keys and permutation bits. And earlier, this randomness was known. Gobbling is to hide these permutation bits from the gobbler. Instead, you secret share these permutation bits as well between the gobbler and the evaluator, and then they jointly generate the gobbler circuit in a distributed manner. So there's a lot of details here that are interesting to work out, but skipping over them for right now. What this achieves is that now the gobbler, even if he selectively gobbles certain rows without, he gobbles certain rows incorrectly. If the evaluator fails at any point, if she aborts on the 3rd row, without knowing that permutation bit, the gobbler can't deduce what underlying value this corresponded to. So quickly going back, we had that selective failure attack, which gives the gobbler information if he has his permutation bits, which can unmask those masked values, and he can use that to reveal the underlying wire value. So with the secret shared bits, this is not a concern anymore. And that's the main purpose of distributing this gobbling process. Authenticated BitGC also at a very high level, it adopts this 2-step framework to upgrade to malicious security. And specifically what we do here is that the gobbler does not hold the secret key for encryption anymore. It's now secret shared between the 2 parties. So that initial encryption that we had, encrypt that seed, that's also done under MPC. But again, this is just you only encrypt security parameter many bits. This is independent of the actual circuit being computed. And then this leads to both parties holding encryptions of some random seed. None of them see the random seed in the clear. And they both use homomorphic encryption now to expand that encrypted seed into these encrypted bits. The gobbler now does not know the permutation bits, right? Because those were generated from the PRC. Instead, he also only holds permutation encryptions of the permutation bits. But this is still this still suffices for him to generate this GC and the correction bit. And the details of this you can find in the authenticated BitGC paper. So from here, more or less, it proceeds the same way. He'll use the encrypted bits. He'll compute the correction bit, send over just the correction bit, and the gobbler and the evaluator will use that to fix the GC, and then she'll use her input keys to decrypt. Again, there's also a correctness check at the end to make sure that the gobbler didn't like flip any of those bits that he was supposed to send. This follows the same blueprint that I described earlier, except now instead of holding XOR shares of the of the underlying wire value, the bodies now hold encryptions of the underlying wire value. Again, by point and permute, the evaluator holds the masked value for intermediate wires in the clear, but she also holds encryptions of the permutation bits. So homomorphically, she can use that to obtain an encryption of the underlying wire value. The parties want to check these relationships, and they both hold encryptions of these wire values. I just said that the evaluator holds it. The gobbler can also hold them with just one bit of communication by using similar masking, unmasking tricks. By the way, this is why the authenticated protocol, instead of using one bit of communication per gate, it now uses 2 bits of communication. Still a lot better than 200. And now they want to check that these gate constraints. So that again that reduces to checking that a single equation holds, and that this chi1 times this relation plus chi2 times this relationship is an encryption of 0. So the entire authentication check is just reduced to checking that a single ciphertext decrypts to 0. Since they hold shares of the secret key, this also needs to be done under MPC, but it's just a single check. So it's still cheap compared to the total cost of the GC. And this turns out to be maliciously secure, and this is what BitGC and authenticated BitGC give us. These are the works that I referenced in my talk, and I think we have some time for questions now.
Thank you so much, Nakul. Yeah, let's open it up for anyone who has any questions. You can please type it in the chat or raise your hand and speak up. So, Nakul, do you have any idea about the compute cost as far as homomorphic encryption goes, like CPU RAM?
I actually don't. It should be easy to get that number. I just don't happen to have that. We could look at that after this. But I will say that the reason that I emphasize that this is also just constant homomorphic operations per gate is that it's actually been known for a while that there are ways to do this succinct gobbling, where your communication it doesn't even have to be number of bits of the circuit. It can be like logarithmic in the circuit size. But those are like really computationally expensive. Those are like, they don't even intend to be practical. The point is that this protocol, it does intend to be practical. But yeah, it's a good idea to get some kind of estimate of the exact computational cost. I'm not sure.
And in terms of authentication, I'm just wondering generally, is are authentication protocols like sort of independent of the garbling protocol? So you can use one authentication as a drop-in replacement in something else? Are they kind of like, is it kind of a Lego, or is it something specific to a specific garbling protocol?
That's a great question. So there are ways. There is a black box compiler for gobbling to make something from semi-honest to maliciously secure. That introduces a pretty large overhead. It introduces a multiplicative overhead of a statistical security parameter, which is like 40. So there's a way to make something, make a gobbling protocol that's semi-honest, make it malicious with a 40x overhead in communication. Authenticated gobbling, this framework that I introduced, the idea is that in principle, this can be done with like almost no overhead. And unfortunately, there's no black box way to do it for protocols right now. It's like every step that you're doing, you're now replacing that generation process and you're distributing it between two parties, and you're trying to see if you can still somehow do it in an efficient way. So to answer your question, right now, no, there isn't like a drop-in replacement, but there is like a framework that morally speaking, it has extended a bunch of different works. And when there's a new semi-honest protocol, you would hope that adopting that authenticated gobbling framework might get you a maliciously secure version for not too much extra cost.
Thanks. Any questions from anyone? Andrew,
Yeah,
go ahead.
Yeah, I was wondering about the you mentioned that the upfront communication cost, the GSW ciphertext, I think it is quadratic in the size of the security parameter. Is that which security parameter is that? Statistical or
So
computational?
computational. Here, everywhere that I use
Okay,
lambda, I mean computational, and we would set lambda to be 128 here.
gotcha. Okay.
Yeah, I will say that there's big O notation for the size of a GSW ciphertext. It's definitely hiding a lot of constants here. So
Mhm.
the exact concrete cost for this seed, it's not yet known. This protocol has not yet been implemented.
Gotcha. And I think I might have asked this before, but do you know this is a two-party protocol in particular,
Yeah,
right?
yeah,
So there's no general. Do we know about
it's
whether
not
this is
known yet.
generalizable to n parties yet? Not known yet. Cool.
Yeah, it's not known yet. There's no clear reason that I mean, in the paper, there was no clear reason or clear difficulty expressed in extending it to multiple parties. Right now, we don't know how to do it. Gobble circuits in general, though, it's known how to extend them to multi-party computation in a bunch of different ways, both semi-honest and authenticated. For this specific work, it's not yet known.
Gotcha. Um, Shoot, I think I had another question, but I forgot what it was.
Yeah, no
Anyway.
worries. Whenever it comes back to you.
With that generalization, Nicole, do you expect the pre-processing, the size of these pre-processing artifacts to go up if you have
Yeah.
multiple parties?
Yeah.
Okay.
Yeah. So one framework for doing it is where in your gobble circuit itself, you kind of extend that to hold something that you authenticate from each party. So your gobble circuit size actually scales linearly in the number of parties that you have. And in that setting, I would expect the pre-processed cost to increase for like general protocols. But maybe for this protocol, since it's like completely independent of the circuit size, it's just an encrypted seed. And from that, you can just like extract as many random bits as you want. Maybe it's independent, but I don't want to conjecture about something that I haven't looked into much. That's a good question though.
I remember what my question was.
Yeah, go
So
ahead.
I think I heard you mention, I think I heard it elsewhere as well, maybe, but I just want to clarify the GSW ciphertext, the upfront communication stuff. That's reusable between like different circuits, different sessions, and everything. So is there just like one fixed sequence, and like that is the GSW ciphertext for that security parameter, I guess?
Yeah, so that's just an encrypted seed, and then that communication can be reused, but it would incur more communication. Oh, sorry, that communication can be reused, but it would incur more computational costs every time you want to run another session and generate more encrypted random bits. But once you have this seed exchanged, from there you can generate arbitrarily many encrypted random bits. So yeah, that communication could be reused across multiple
Oh,
sessions.
but it's specific to the two parties.
Specific to the two parties.
Right, yeah, because I was wondering, like, can we, for practical purposes, can we just like embed this ciphertext in the software? But that's so that wouldn't make sense, right? Because it's like the two parties have to come up with this. Do
Yeah,
they?
yeah.
Yeah.
I mean, definitely for the authenticated version they do. For the semi-honest version, I'm not thinking if uh, that seed is known to one party and it's just like generated ahead of time and paste in. Uh, yeah, I want to say that It's specific to the two parties, but this is another thing that I'm going to make a note of to think about later.
Okay, cool.
Yeah, definitely the communication can be reused across multiple sessions though. Yeah. And importantly, that can be done before you know the circuit you want to compute or have your inputs for the function, or just like have an upper bound on the size of the circuit and produce enough random encrypted bits.
Wait, the size of the circuit is an input that determines the size of
Yeah,
the
so
ciphertext?
it doesn't determine the size of the ciphertext. All I'm saying is that
The
you
details.
can do the computational cost of generating that many generating those many encrypted random bits. That can be done. The computation of doing that can be done before even knowing what circuit you want to compute. But the communication of just the ciphertext, yeah, it doesn't even need an upper bound on the circuit size.
Oh, so sorry, what was the size of the circuit makes an impact on, like, the upper bound on the size of the circuit is the upfront cost, the
It's
upfront
the
computation cost before you
yeah,
know
the
the
upfront
size of the circuit.
computational cost.
Yeah, gotcha.
Correct.
Yeah.
Yeah.
No, that makes sense. Yeah.
Because you're given a PRG, you can decide how many times you want to use it to generate more random bits, right?
Yeah, that's analogous to, you know, in sort of regular garbling. Yeah, or in authenticated garbling at least.
Oh, yeah.
That you have these triples that you prepare ahead of time. Yeah.
Exactly that.
Got you. Cool.
Yeah.
All right, we are right on time. Nakul, this was fantastic. Thank you so much for your time.
Of course.
For anyone who may have follow-up questions later on, you can ask it on Discord. We're all there. So thanks again, Nakul, and thanks everyone for being here. And yeah, catch you guys later.
Yeah, thanks everyone. Hey, Ali.
Hey, Nakul, thank you so much. Let me just stop the recording.